Dear students, today we shall learn how to create relief by drawing profiles. First of all, we need to know what is the meaning of relief and why we need to draw them. The surface of the earth is covered by mountains, valleys, plains and seas. These elevations and depressions of the earth's surface are technically known as relief of the earth. It is important to understand these relief features which are spreading in large extent on the surface of the earth. Therefore, we need to map them to understand their forms, features and extent. The relief features are also synonymously referred to as topographic features. The topographic maps or relief maps represent topographic or relief profiles. A relief profile is a cross-sectional view along a line drawn through a portion of a topographic map. In other words, if you could slice through a portion of the earth, pull away one half and look at it from one side, the surface would be a topographic or relief profile. Not only does constructing a topographic profile aid in understanding topographic maps, it is very useful for geologists when analyzing numerous problems to see hazards such as landslides etc., and draw conclusions about the strike and dip of the geology beneath the land surface. This is a figure which shows a simple profile of an area. To construct a topographic profile, you must first decide on a line that is of interest to you. This could be an area of your interest, whether you want to make a recreation there or you may want to make some settlement planning or construct some dam etc. Therefore, you need to know how much depth it is expected to be, a line that shows the maximum relief in the map area or any other area in which you are interested. Once you have determined where you want to draw your profile, use the following guidelines to construct your profile. Observe this figure carefully and you will see that this is a simple map of contours. Using this map, we shall draw the profile of this region. To draw the profile, you have to first tick the points with a pencil on the lines of your interest lightly on your map. Place a blank piece of paper along the line you have drawn. You may have to fix the paper to the map using drafting tape to keep them together from moving relative to one another. On both the blank paper and the map, mark clearly the starting and ending points of your line of section. Below these marks, write down the elevation of the starting and ending points of your section. Make a tick mark wherever the paper crosses a contour line on the map, making larger ticks for the index contours and smaller ticks for the intermediate contours. Write the elevation of the index contours below their ticks on your paper. You might want to start off writing the elevation of the intermediate contours as well to avoid confusion, but it will soon become tedious. Make a note of the highest and lowest points on the profile for later use. Be sure to keep track of the number of intermediate contours between the major contours. If there are more than 4 intermediate contours, it means that there has been a change in slope and you need to check to see if you have crossed a hill. Once you are certain you have all the appropriate tick marks and elevations, remove your paper from the map. Get a piece of graph paper that is at least as long as your line of section. If you are using a map with a scale of 1:24,000, you will want to use graph paper that has 1-inch grids to make work easier, and mark the starting and ending points of your line of section on the graph paper. Draw vertical lines above your starting and ending points. These will be the boundaries of your profile. Use the maximum and minimum elevations along your line of section to determine how long to draw these lines. For example, if your minimum elevation is 4,320 feet and your maximum elevation is 6,280 feet, you will want your vertical line to be at least 2 inches long. Remember that 1 inch equals 2000 feet on a 1:24,000 scale map. The difference between 6,280 feet and 4,320 feet is less than 2000 feet. So, it would be possible to draw your profile in just 1 inch. However, it is much easier to construct a profile if your lowest elevation is a multiple of 2000. So, you would want to start at 4000 feet and go to 8000 feet, that means 2 inches. Beginning with your starting elevation, go directly above the tick mark on your paper and make a small dot on the graph paper at the corresponding elevation. If your graph paper has 1 inch squares divided into tenths, each smaller square will represent 200 feet of elevation change. Each index contour should lie along a horizontal grid line. Make a small dot for each tick mark on your paper. Connect the dots on the graph paper and you have a topographic profile. This figure shows the profile of a region drawn from the contour map. Similarly, various shapes of profiles emerge by drawing from different contour maps. And after drawing the profiles, it is necessary to study the kind of profile. This is useful for many applications. For example, soldiers may need to determine not only the height of a hill, but the degree of the hill slope as well. The rate of rise or fall of a terrain feature is known as its slope. The speed at which equipment or personnel can move is affected by the slope of the ground or terrain feature. This slope can be determined from the map by studying the contour lines. The closer the contour lines, the steeper the slope. The farther apart the contour lines, the gentler the slope. 4 types of slopes can be distinguished. Gentle slopes, where the contour lines showing a uniform gentle slope will be evenly spaced and wide apart. The second kind of a slope could be a steep slope. In such a slope, the contour lines showing a uniform steep slope on a map will be evenly placed but close together. Remember, the closer the contour lines, the steeper the slope. The third kind of a slope is a concave slope. In such a slope, the contour lines on a map will be closely spaced at the top of the terrain feature and widely spaced at the bottom. The fourth kind of a slope is a convex slope. The contour lines on a convex slope on a map will be widely spaced at the top and closely spaced at the bottom. Another important feature of drawing of profiles is that how to represent the relief using appropriate cartographic methods. Let us see how to use such cartographic methods. The terrain or relief is an essential aspect of physical geography, and as such its portrayal presents a central problem in cartography and 3D visualization. The most obvious way to depict relief is to imitate it at scale, such as molded or sculpted solid terrain models and molded plastic raised relief maps. Because of the disparity between the horizontal and vertical scales of maps, raised relief is typically exaggerated. On flat paper maps, terrain can be depicted in a variety of ways, such as hill profiles, hachures, contour lines, hypsometric tints, shaded relief, physiographic illustrations, forms and associations. Hill profiles. You can see in this figure the hills drawn in areas where the terrain is undulating. This is the most ancient form of relief depiction in cartography. These are simply illustrations of mountains and hills in profile placed at appropriate places and generally on large scale maps. They are seldom used today except as part of an antique styling. Hechures. You can see in this figure that hechures are short broken lines used to show relief. Hechure representation of relief was standardized by the Austrian topographer Johann Georg Lehmann in 1799. Hechure is sometimes used with contour lines. They do not represent exact elevations, but are mainly used to draw large rocky outcrop areas. Hechure is used extensively on small scale maps to show mountain ranges, plateaus and mountain peaks. They are also an older mode of representing relief. They are a form of shading, although different from one used in shaded maps. You can observe this figure. They show the orientation of slope, and by their thickness and overall density they provide a general sense of steepness. Being non-numeric, they are less useful to a scientific survey than contours, but they can successfully communicate quite specific shapes of terrain. The contour lines or the isolines. The contour lines are the lines joining all points having the same elevation, and they are the most common method of showing relief and elevation on a standard topographic map. Most 18th and early 19th century national surveys did not record relief across the entire area of coverage, calculating only spot elevations at survey points. The United States Geological Survey USGS topographical survey maps included contour representation of relief, and so maps that show relief, especially with exact representation of elevation, came to be called topographic maps or topo maps in the United States, and the usage has spread internationally. Contours make it possible to represent the height of mountains and steepness of slopes on a two-dimensional map surface. The most distinctive characteristic of contour lines is that the three-dimensional shape of the earth surface is modeled in two-dimensional map surface. The elevation represented by contour lines is the vertical distance above or below sea level. There are three types of contour lines used on a standard topographic map, such as index contour lines, supplementary contour lines and intermediate contour lines. All these contours or isolines show equal elevation. This is the most common way of numerically showing elevation and is familiar from topographic maps. This figure shows the different types of contour lines, the intermediate, supplementary and the index. The index contour lines starting at 0 elevation or mean sea level, every fifth contour line is a heavier line. These are known as index contour lines. Normally, each index contour line is numbered at some point. This number is the elevation of that line. The second kind of a contour line is the intermediate contour lines. These contour lines falling between the index contour lines are called intermediate contour lines. They are finer and do not have their elevations given. There are normally 4 intermediate contour lines between index contour lines. The third kind of a contour line is the supplementary contour lines. These contour lines resemble dashes. They show changes in elevation of at least one half of the contour interval. These lines are normally found where there is very little change in elevation, such as on fairly level terrain. There are several rules to note when viewing the contour lines on a topographic maps. Observe this figure carefully. The rule of V's. Sharp pointed V's usually are in stream valleys with a drainage channel passing and V's pointing upstream. This is a consequence of erosion. The second rule is the rule of O's. The closed loops of contours are normally uphill on the inside and downhill on the outside, and the innermost loop is the highest area. If a loop instead represents a depression, some maps note this by short lines radiating from the inside of the loop called hachures. The other important feature of the contours is that spacing of the contours. The close contours indicate a steep slope, distant contours a shallow slope. Two or more contour lines merging indicates a cliff. The other form of representing profile is the hypsometric tints. Hypsometric tints or relief tint is a method of showing relief by color. It is a method to represent contours in different colors for each band of elevation. Each shade of color or band represents a definite elevation range. A legend is printed on the map margin to indicate the elevation range represented by each color. However, this method does not allow the map user to determine the exact elevation of a specific point, but only the range. They can be used to depict ranges of elevation as bands of color, usually in a graduated scheme or as a color ramp applied to contour lines. A typical scheme progresses from dark greens for lower elevation up through yellow, browns, etc. on to greys and white at the highest elevations. Hypsometric tinting of maps and globes is often accompanied by a similar method of bathymetric tinting to convey depth of oceans, lighter shades of blue representing the shallower waters such as the continental shelf, and darker shades to represent deeper regions. You can see these figures representing the different tints. The next method of representing relief and presenting the profiles is the shaded relief method. This method indicates relief by a shadow effect achieved by tone and color that results in the darkening of one side of the terrain features such as hills and ridges. The darker the shading, the steeper the slope. Shaded relief is sometimes used in conjunction with contour lines to emphasize these features. Hill shading simulates the cast shadow thrown upon a raised relief map, or more abstractly upon the planetary surface represented. The shadows normally follow the convention of top left lighting, in which the light source is placed near the upper left corner of the map. If the map is oriented with north at the top, the result is that the light appears to be coming from the northwest. Many people have pointed out that this is unrealistic for maps of the northern hemisphere, because the sun does not shine from that direction, and they have proposed using southern lighting. However, the normal convention is followed to avoid hill confusion. You may see these figures carefully. The figures show that the light coming from the northwestern direction and falling towards the southeastern direction. Traditionally, relief shading method used to be drawn with charcoal, airbrush and other artists' media, Shaded relief is today almost exclusively computer generated using digital elevation models, resulting with a different look and feel. Much work has been done in digitally creating manual hill shading techniques. The use of illumination and shadow to produce an appearance of three-dimensional space on a flat surfaced map closely parallels the painting technique. Shaded relief method today can be created digitally using a digital elevation model or what is called as DEM. The DEM may be converted to shaded relief using software such as Photoshop or ArcGIS, etc. The next method of relief representation is the physiographic illustration. This technique was pioneered by Hungarian American cartographer Erwin Reis. This technique uses generalized texture to imitate landform shapes over a large area. A combination of hill profile and shaded relief has been adopted, and this style of relief representation is useful in illustrating geomorphological patterns. And the last method of relief representation is what is called as the forms and associations. Form lines are not measured from any datum plane. Form lines have no standard elevation and give only a general idea of relief. Form lines are represented on a map as dashed lines and are never labeled with representative elevations. We may conclude that drawing of profiles and representing of relief was one of the challenges for cartographers to bring the 3 dimensions of the earth over the 2 dimensions on the paper. But in recent times, with the use of computer aided technology, the profiles can be very comfortably be visualized in the 3-dimension form. Thank you.